Now let's see a free RC circuit. We have a capacitor and we have a resistor. The capacitor is initially charged to, let's say the voltage is V0. We had used I0 there, so V0 is 0. We have charged this capacitor and now what we do? We discharge it. Okay, so this is C, this is R. Let's say this is your I, the natural response. What we get? We get not I. You cannot go by this way. See, here what you will have to do is, let's say the voltage across this is V. Okay, this is the voltage. Now let's do KCL at this point. This is your node. So one current flows in this direction, not in this direction. See, in this direction. So this is this direction, this is this direction. So what we get is, current in capacitor is C dV by dt. This is the current, and what is there? Plus V by R. Okay. So for KVL we were using this. For KCL we say this is the current going through this direction and this is the current going through this direction. They have to be in equilibrium. They have to be equal, better to say. So this is equal to 0. C dV by dt is equal to V by R. Sorry, minus V by R. Okay. So this is the equation KCL when we took at this node. This current plus this current equal to 0. Okay. Now from here what you get? C dV by dt is equal to minus V by R. So what you get is dV by V is equal to minus 1 by RC T. So if you integrate it, what you get? Similarly, you get log V equal to minus 1 by RC T. So what do you finally get from here is V is equal to e to the power minus T by C, minus T by RC. Okay, and you will have a constant. Again you put T equal to 0, that will be equal to V0. So finally what you get is, this is V0, okay, for T equal to 0. So this is the equation for this. What is the time constant here? RC. There it was L by R, here it is RC. The expression is same, so you'll have same IT. If you get this picture, this will be this, not this. If you plot, this will be at T equal to infinity, this is 0, at T equal to 0, this is T, this is I. So at T, this is V0, and at infinite time you have this voltage equal to 0. Okay, so we have seen capacitor's natural response. Now let's see what if a voltage source or a current source is applied. Let's see the forced response of RC network, the way we saw for RL network. Okay, the circuit will be like this. Let's say our voltage source is V. We have a switch here, then R, and then we have a capacitor. Let the voltage across the capacitor be VC, the AC voltage be VC, this is R, this is closed at T equal to 0. Okay, now this is your VC. Let the current be I. Okay, so the equation will be, see, minus V plus RI plus what you have? VC, that voltage, equal to 0. Or you can say RI plus VC is equal to V. RI into plus VC is equal to V. And you know for capacitor, I is equal to C, the voltage across the capacitor, that is VC here, by T. This you know. C dV by dt, V here is VC across capacitor. So let's put it in this equation. So this becomes R C dVc by dt plus Vc equal to V. This is the equation that governs this particular circuit. Now you know that the natural response voltage is equal to V0 if the initial condition is V e to the power minus t by tau, where tau is RC. This we have seen, the natural response. What about forced response? See what happens from this equation. Also you can see at t equal to infinity this becomes equal to this, that is at sufficiently large, after sufficiently large time, that is t equal to infinity, this current stops and this voltage actually appears across this voltage. That is, the voltage that you will have here will be at this point. Okay, so this voltage will be at this point. So now let's write the equation, this equation. So our voltage, finally voltage that we want to know, this is equal to V0 e to the power minus t by tau, and the forced response voltage, this voltage appears across this. This is a constant voltage source, remember this. So our equation after solution becomes this. This equation, when you solve, this becomes this. Why? This is the natural response and this is the forced response. The way we did in RL circuit, the natural response current and the forced response current. Similarly, here we have the voltage is equal to V0, E minus t by tau is the natural response and V is the forced response. Okay. Now, what we have to find, not V0, sorry, not V0. Let's keep it A here, because our initial conditions are different. There we had taken V0, V initial state condition to be equal to this V0. Here this is not the case. Here we have initial condition to be 0. So here I am taking constant. We will see what value we get. See, I am rubbing this. Now at t equal to 0, our initial condition is V0. Okay. So now let's put this in this equation. This becomes V0. This becomes A, t is 0, so this is 1, and plus we have this voltage V. So here A is not V0, but A is V0 minus V. See, that is this constant is what voltage we had initially minus this voltage. This was the driving force. So A is this. So if you put it in that equation, what we get is V is given as A, that is V0 minus V into e to the power minus t by tau plus V. Okay, or you can take V here. See, we can have this as V0 e to the power minus t by tau, and then we can have our V into 1 minus e to the power minus t by tau. So this is the response for t greater than 0 of a RC circuit when it has a voltage source connected to it. V0 e to the power minus t by tau, V 1 minus e this. Now important to note is, what is the value of the voltage across the capacitor when we have t equal to 0. See, at t equal to 0, this is V0, this is 1 minus 1 0, that is at t equal to 0. I am plotting the graph now. The voltage is to time graph. See, this is voltage, this is time. So at t equal to 0, we have here somewhere V0, and at t equal to infinity, see, when you put infinity, this is 0, this is 0, so this is V. That is at t equal to infinity, you have this figure. So if this is V, this is the plot. Okay, clear? Here you do not have from 0 to here, you have initial condition and then up to this point. So we have V, from here we can get what is I. Let's see. So this is the voltage across the capacitor, this voltage. So we have used C, so let's use that subscript C. So Vc is this as a function of time. Okay. Now what is I as a function of time? This is, we know C dVc by dt. This you know about it. So if you take this is 0, this is a constant. So what you will have to do is take this as derivative. We have to take C dVc by dt. See, not this one. This is constant, so 0. When you take this, what you will get? You will get V0. This is C into V0 minus V by RC. This is RC. So this is, you get here, and you get minus also, minus e to the power minus t by tau, or you can say this is C cancel. So it is V minus V0 by R into e minus t to the power tau for t greater than 0. This is your current in the circuit. Okay, this. So this is the expression for voltage across the capacitor, and this is the expression for current in the circuit. Now from here, what we see, that at t equal to 0, if you put t equal to 0, this is V minus V0 by R. That is, the capacitor acts as a voltage source. That is a fully charged capacitor. When you connect it to a resistor, it behaves as a voltage source. And at t equal to infinity, this is 0. See, at t equal to infinity, this is 0. 0 means no current flows. The way we found this value V in the force response. So at t equal to infinity, this is 0. Current stops to flow. That is, the capacitor becomes open circuit. So after some time, that is when you connect the switch at t equal to infinity, for an inductor, the inductor behaves like a short circuit, and at t equal to 0, inductor behaves as an open circuit. While for the capacitor, it is reversed. At t equal to 0, it behaves as a short circuit, and at t equal to infinity, it behaves as an open circuit. This you should keep in mind when you will solve problems. Okay.